Alright guys, you don't know this, but this is round 2. After I did that last video, it failed to save and just sat there, it said saving, and then it just didn't refuse to upload, refused to save as an actual video. So all my stuff is already written here, which is why, well, that's why everything is already written here. So because I have done a video already. So let's get started. All right, on your bell ringer, the radius is given to you as 2.16 angstroms. All right, and again, we're just trying to work through some of these units to really get familiar and stay familiar with those. So the first question is, what's diameter in meters? Okay, so we got to first figure out what diameter and radius, how they're related. Obviously, the diameter is twice the radius. So that comes out to 4.32 angstroms. Okay, y'all correct your bell ringers as you go along here so that you can sort of see where you went wrong if you did go wrong. All right, so 4.32 angstroms, how do we get to meters from there? All right, well, we know that 1 angstrom is equal to 1 times 10 to the negative 10th meters. So that 1 meter is therefore 10 to the positive 10th angstroms. Okay, that's how that deal works, except that's a 10, not a scribble. All right, so we use that conversion factor here, and that's always true. If something's 10 to the negative 6th meters, it takes 10 to the positive 6th of them to make up that original unit. Okay, so we convert that here, 10 to the negative 10th meters. All right, and then we say we need to make a chain 0.75 meters long. So how many atoms of rubidium is that? Okay, so 1 atom of rubidium is that many meters. The meters cancel, and we get 1.74 times 10 to the 9th atoms. Okay, so when you divide by a number that's got a negative exponent, it's actually makes it a big number because we're dividing by a very small number. All right? And then we want to know how many moles is that. Okay, you guys are familiar with this, so I won't spend a whole lot of time, but 1 mole, 6.02 times 10 to the 23rd atoms. The atoms cancel out, and we end up with 2.89 times 10 to the negative 13th moles. And then we're curious how many grams that is. So we really could have done boom, 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 all in one conversion, but we're breaking it down into steps. All right, 2.89 moles. Each mole is 85.5 grams rubidium. We looked that up on our periodic table. And we get 2.47 times 10 to the negative 11th grams of rubidium. So that's how many grams of rubidium we need to make a chain 0.75 meters long. That's 1 atom thick. All right. So if y'all will get out your books, flip over to page 121. We'll get into chapter 5 here. All right. And so we need to know where we're going before we get started. And so where are we going? We need to be able to explain the octet rule, okay, and our Latin scholars that you guys all are, you know that's got something to do with 8, and we'll see why in just a minute. And that's really all we're going to get out of section 5.1, which is why we're also going to do part of 5.2. It's too much in 5.2 to do all of it, all in one lecture, but it's we'll do part of it, and then we'll pick that up and slide into 5.3 next time as well. We won't be able to finish that next time either, I don't think, just kind of gauging by how long it takes. But details of ionic bonding and write formulas for ionic compounds that are formed. Given a chart with common oxidation states. We talked a little bit about oxidation states before. We'll talk a lot more about it now and what that means. For transition metals, give names for ionic compounds formed from given elements using the stock system and the older system based on Latin names. We'll talk about what all that means. Explain the terms lattice, energy, and hydrate. Obviously, we'll need to just talk about that. And then explain why ionically bonded compounds tend to be brittle and dense and have high melting points. All right, so let's dive in here, okay? I think it'd be good for you guys to kind of write down what we got going on right here. So we have got these 1, 2, 3, 4, 5 topics or general broad concepts that we want to always be coming back to. Electrical attractions and how they affect things. What's going on with the electrons. We want to minimize energy when we're talking, or rather the atoms and compounds want to minimize energy. Nature itself wants to minimize energy. Whole number ratios and modeling. And just remember that these whole number ratios, yeah, they make sense to us. Obviously, you can't have half of an atom of lithium. What would that even look like, right? But if you don't know that things are made up of atoms, you don't know that things are in whole number ratios. So one of the main arguments for things being made up out of atoms was that they were always in whole numbers. And so they said, well, heck, I mean, I guess they got to be made up of something that's indivisible, as it were. Okay, of course, we know that they're somewhat divisible. We can pull electrons off. We can even knock protons and neutrons or add protons and neutrons. But generally speaking, in chemical processes, we're never going to be chopping atoms up or changing anything other than those outside electrons. All right, so I would underline those. Obviously, I've got the word reiterate over here because I think it's important. So that might show up on a quiz or test sometime. And again, it's just they're a helpful framework for you to start to think through some of the overarching narratives that we start seeing in our chemistry book here. Okay. Let's see. All right, so we see atomic bond hold atoms together in rigid, extended, regular structures of crystal lattices. Okay, and crystals are just regular, repetitive structures that will sort of make bigger and bigger crystals. If you guys have ever done one of those little trees that you put it in the solution, it sucks it up in there, and then they form crystals on the outside, and it grows like these sort of fuzzy-looking, shiny crystals on the outside. That's what's going on. They just, you'll end up with a salt crystal that's just bigger and bigger and bigger, and it's just a repetitive structure. But anyway, we'll talk about that some more. So we have 3 bonding types: ionic bonds, covalent bonds, metallic bonds. Okay, that's all there is to really say generally about bonding. All right, octet rule. Jump right down to it. Okay, in other words, atoms tend to gain or lose electrons. Got kind of a shine on y'all there. Sorry. Let's see if I can fix that some. Maybe that's a little bit better. They tend to gain or lose electrons to achieve an octet of electrons in the highest energy occupied shell. So let's just stop right there. Flip back to our deal back here. Okay. And so when we're talking about that highest energy shell, all right, remember that these guys have got that D shell, okay? And we've got 1, 2, 3, 4, 5, 6, 7, 8. It's those 8 that are in the higher shell. So these guys, what are they? These are 1s2, 3s2, 3p6, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10. Remember that? Okay. So even in these guys that have those d electrons, they're trying to make an octet out of their 4s and 4p guys here. Okay, and that's what they're gaining and losing electrons to make happen. Okay, and then we'll just go ahead and talk about it. We've got our plus 1s right here, because remember they like to lose 1 electron. Okay, plus 2s, they like to lose 2 electrons to get to that noble gas over here. These guys are -1s because they like to gain 1 electron, and electrons are negative, so it's a -1. They like to gain it to get to right here. Gain 2. Many of these like to gain 3. Some of these down here act a little bit weird because they got so many electrons. The shield effect and all sorts of things make them act a little bit differently. Okay, and then we've got some in here that are kind of, and even nitrogen sometimes when it's bonding acts like it gains electrons. Okay, so we'll get into all what guides those things, but the ones we can be really sure about are the +1, +2s, -1, -2s, generally -3s. Okay, and where it's ambiguous, guess what? I'm going to tell you what you need to do, or you will know what its oxidation state is. Okay, we're not going to ask you to memorize a whole bunch of rules. It's pretty straightforward. Okay, so also we need to say the other thing that's different. Where did we say obvious? Obvious main group exceptions to the octet rule are hydrogen and helium. Sorry, I'm off the screen there. Okay, hydrogen and helium. Well, why is that? They're satisfied with a single pair of electrons in the 1s subshell because there's only a 1s1 and 1s2. That's all there is. They don't have 8 because you need a 2s and a 2p to get 8. They only need 2 because they don't have that second subshell. Okay, so that, to me, I've never found that to be like hard to remember because, you know, that hydrogen's not trying. Where would it even put 8 electrons? It's only got one deal. All right, so let's think about what's going on in that situation. All right, so let's go back to what you guys have seen before, and we kind of beat into your heads is not how atoms look. That's not how electrons look around an atom. Okay, well, we're going to use that because this is going to lead us into how we're going to do Lewis diagrams later. All right, so what do we have? Let's take an example, and let's look up sodium here. Okay. Sodium is number 11 on the periodic table. And so we're just going to fill them up. We're in as if they were orbits, okay, as if they were nice round shells. So what do we have? We got 1, 2. And then our second shell has a 2s and a 2p, so it holds 8. 1, 2, 3, 4, 5, 6, 7, 8. All right, but we need 11. That's 2 and 8 is 10. We've got 1 extra electron right here, all by his alone. Okay, so he does not have 8 in his outer shell. Then we've got lonely old fluorine here. Okay. And fluorine is number 9. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Well, guess what? There's a nice electron-shaped hole right here. Okay. And we want, fluorine wants more than anything else, just a simple electron to finish that out. Okay. Well, fluorine wants 1. Sodium wants 8 in his outer shell. He's not going to get 7 more. That's just crazy to think about. So what happens? They come together and they make a deal. Fluorine says, "I want 1. You want to give 1 up. Let's just hang out." All right. So this electron actually kind of gets pulled over to fluorine and fills that void right here in the orbital. Okay. Well, when he loses 1, guess what? He becomes a +1. Okay. And when fluorine gains 1, he becomes a -1. And we see that opposites attract as far as electrical stuff goes. Okay. So that plus and that minus are drawn to one another, and these guys start to hang out pretty closely. Okay, and that's what he's kind of talking about in earlier. They like to stack and like to be as close as they can get. All right, so those orbitals are kind of bumping up against one another, and they're like excuse me, they're like two balloons that are kind of, they're both getting sucked toward an air vent. When they kind of bump into one another, and then they kind of bump, and then they bump, and they bump, and they kind of just sit there as close to one another as they can, because that air current or whatever is pulling them. All right? That's what these do. They're attracted to one another, and they just bump, and they sit like magnets, like round magnets sitting on top of one another. Okay? And you can pull them apart, but it takes energy to pull them apart, and they just want to bump right back together again. Okay? And the overall driving thing is that when you put a sodium and a fluorine next to one another, they have a path towards a lower energy situation in which sodium gives up one and fluorine gains one, and then they're attracted to one another, they move together and sit. Okay? All right? So let's look at another situation. Okay? We want to talk about magnesium and chlorine. All right, so flip back to your periodic table. What do we have? Magnesium, it's 12. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 in those inner two. And then he's got, on his third shell, he's just got 2 electrons. Okay? And chlorine, like we just talked about, well, chlorine's not just like we talked about, but it's in the same family, in the same group as fluorine. Okay, both halogens. And what's chlorine? Chlorine's 17. So we got 2 here and then 8, so that's 10. And then we've got 7 in the outer shell. So just like we had 7 in the outer shell for fluorine, we got 7 in the outer shell for chlorine. Okay, and that's why they're both -1s, because they like to absorb 1 electron and become a -1. All right, magnesium's got 2 to give up, and chlorine's only got 1 space to put it. So chlorine calls her twin sister and says, hey, she's got a need for an electron too. You've got 2. Magnesium's saying, hey, I got to sell both of these. All right, so they get together. One comes over here, and the other one comes over to here. But these are now attracted to this magnesium, and they hang out super close to one another. Okay? Actually, these are both negative, and that's a positive, so it's really more like this. They minimize their contact with one another because they're both negative. All right? But then when you get other guys in there, you get another magnesium chloride in here somewhere. That changes how all the things, and that's kind of what he was talking about. They stack in special ways. Okay? So this is probably not super right, but the point is that these guys are both negative, so they move away from one another. Okay? And they're attracted to this one, so they move as close in as they can without their orbitals actually overlapping. All right? And also the point is that we can look at this and we can say that this is a 2 plus and a 1 minus and a 1 minus. Okay? So we have 1 2 plus guy here and 2 1 minuses right here. So we have an overall 2 minus and a 2 plus, and the whole deal comes out to be a 0. All right? And that's pretty straightforward. So if we don't have to do this every time. That'd be a long process, okay? So what can we do? Well, we look at their oxidation states, the number of electrons they prefer to give up. Okay, like we saw, sodium preferred to give up just 1. And we could look back at our ionization energies, and we would see a big jump between losing this electron and then losing one of these, because these are our what? Core, and these are our valence. All right, just like we talked about on that test. All right, so we look at lithium. He's in the first column, the first group. Oxygen is in the second group to the left of the noble gases. All right, so he's a -2. And so we only need one of these to absorb 2 electrons from 2 separate lithium ions. So we know that this is going to form an Li2O. All right? And we can do any number of combinations and end up with a similar situation. All right? A +1, a -1. It's going to be a 1-to-1 ratio, KCl. Rubidium, Cl. Sodium, Cl. You know, table salt is NaCl. Well, it's 1 Na and 1 Cl because this is a guy who wants to only give up 1, and he only wants to absorb 1. So perfect, match made in heaven. Okay? 1 and 1, lithium fluoride. They always form Li1, F1, which we don't write those subscripts, so it's just LiF. All right? And if we have a 2, we know we're going to need 2 of these, lithium 2 oxide, sodium 2 oxide, Na2O, K2O. Okay? But since these guys want to give up 2, we only need 1 of these for 1 of these. Magnesium oxide, +2, -2. All right, so it's pretty straightforward, especially when we're dealing with these. All right? And when we don't know what they are, we'll generally be told what they are. Oh, and just right here in your book, he kind of goes through specifically what's going on with some of these orbitals, like which orbitals it's going into and what it does to complete those. So you can look at that. It's basically what we were drawing right here, except a little bit more detailed about the orbitals. All right? So we just need to remember that ionic bonding is typically thought of as a process of electronic transfer. That's going to be important because covalent is electron sharing, not transfer, sharing. Okay? Now, how much of this is metaphor and how much of this is actually what happens with the electrons, we're going to kind of know a little bit more about that when we finish up our chapter. All right, so let's talk through some of these and why they've got to be what they are. All right, so we look right here. All right, so why do we need 3 of these and 2 of these? Well, if we look where phosphorus is in the periodic table, we'll see that it's a 3+, a 3-, and berylliums are a 2+. All right. So if we do just 1-to-1, we end up with a 2+ and a 3-. Doesn't come out to 0. We can't add half a beryllium, so we add a whole beryllium. So now we got 4+, giving up 4 electrons, and a 3-. Still can't balance that. So we add another phosphorus. Now we've got 6 electron holes we need to fill, and only 4 to fill it. So we add another beryllium. So now we got 6 giving up, 6 receiving, beryllium 3, phosphorus 2. So Be3P2 right here. Okay, pretty straightforward. All right, and then he gives us a transition metal one right here. Move down. Okay, transition metals right there. Okay. All right. So if you're just told it's a 3+, you just go with it, okay? Because they've discovered these things sort of, and then now know what typically they oxidize and under what circumstances. And we'll talk about that in just a second when we're talking about copper oxide. Okay. So we've got to do the same thing here. This is a 3 and a 2, except this is a 3- and a 2+. Now we got a 3+ and a 2-. We do the same thing, and it ends up Fe2O3. And y'all can pause that and work through that if you think that will be helpful. All right. So how do we tell when we've got a situation like this with the iron? We obviously need to be told that it's got an oxidation state. Well, sometimes they have more than one oxidation state. Well, what do we do with that? Okay. Well, we've got a way of naming it. Okay. Copper 1 oxide means that this copper has a +1 oxidation state. So it takes 2 of them to cancel out the 2- that the oxygen is. All right, and then we have an alternate situation, which we've got copper 2 oxide. Okay, and that means it's got a +2. So what does that mean? It's just going to be CuO, a +2 and a -2. Okay, this is cuprous versus cupric. Okay, this is the one that I think is the most descriptive and the easiest to remember, and so it's a double winner. So we'll be focusing on that. Okay, and you can see, you can kind of look right here. This substance is a red powder, talking about Cu2O, and one's a black powder. So look at how different these two things are. Okay, and how different their individual sort of cell structure looks like. Okay, and obviously we're using cell in the, not in the biological term here. Okay, but sometimes it's not obvious. Okay, what they're going to form, and so a question that I have always had is, well, how do you tell or control or do? How do we even know this? Well, they've just discovered over the years that this temperature leads to primarily a copper 2 oxide, whereas this temperature probably leads to a copper 1 oxide, and it might be a 70-30 mix of both of them, and then you have to do some sort of purification, filtration, dissolving in one acid that doesn't dissolve the other, and then separating them. So there's all these tips and tricks that they've learned in sort of the industry. If you're in the chemical production business, like we buy hypochlorous acid for disinfecting water that we pump out of wells for drinking water in Flowwood, and it's produced on a mass scale under very specific circumstances, and it's just HCl. It's just the same thing that's hypochloric acid, but except we're doing hypochlorous acid because it works a little bit differently. So anyway, point is you have to be able to control for those things and then produce which one you want. All right, this might be super useful. Well, this one's not useful at all. I don't know, but there are chemists who do, and chemical engineers who know this stuff all the way down to the very bottom. So I think that's where we're going to leave it. Right? Okay. Just also, these are called binary formulas because there's just 2 of them. It's just copper and just oxygen. Okay, so that's important to remember when we're calling when we're labeling these things. Again, we're just kind of learning that language. All right, so ionic bonds, transferring electrons. You can't do too complex of things with that before you get into the covalent bonding is the only thing that works. So typically we'll just have 2 formulas, 2 compounds. I don't know if it's always forever like that, but even if you've got 1 magnesium and 2 chlorines, it's still just 2 elements that are involved. Okay, so we'll talk about like sulfuric acid later, which is H2SO4. So you've got H, S, and O, hydrogen, sulfur, and oxygen. That's got to be covalent because it doesn't. Ionic compounds don't do that. They don't do more than 2 elements. Okay. All right. Well, sounds good, guys. I'm going to get your tests graded and back to you just as soon as I can. Hopefully, that'll be before the weekend. You guys be working on your lab reports. Let me know if you got any questions on those. Shoot me a draft if you want me to try and look at it this weekend. I've gotten 1 or 2 so far, and I'm going to look at those and get you feedback on those so you can make the edits before those are due Tuesday. I'm going to get some homework posted tomorrow, or well, for y'all today, and I think I may have to revise because I think we're off a day, but I'll check that in the morning and get that either an email or revise the assignment sheet. I think that's it. And lab reports due Tuesday. Yeah, that's good. So homework, lab reports, and I'll get your test grades up just as soon as I can. All right. Thanks, guys.